Now we come to the next one, 2D elements. This is more interesting now, getting more interesting. And the reason is that now we try to come closer to the physical nature of the model of the building, because one line does not exist, right? Even this cable, which seems to be one line, has a thickness. So modeling of a thick cable, thin cable should not be the same. 2D elements become slightly closer, but not close enough. But for us, it's still okay as long as we understand the limitations of these 2D elements. So now we want to model the surfaces. First we want to model the lines, now we want to model the surfaces. And for that, two-dimensional elements will be used. So there are basically 3 elements, and this is very, very important for you to understand the difference between the 3 elements and when to use them, what are their behavior, and so on and so forth. First one is called membrane. What does it mean, membrane? What do you call it if I want to call it, if I want to give it a geometrical definition? What would be this paper? I know, but what would be, if I want to call it some structural or a geometrical body, what is this? I don't want to call it paper, I want to call it a general statement for things like this. What would I call them? This is a membrane. I can bend it, rotate it, it has no bending stiffness, right? Anything which is very thin and has no bending stiffness can be rolled around, can be folded, can be twisted, can be done anything without breaking, without doing any stresses, without releasing anything, is a membrane. Membrane is a thin object, very thin object, which can be twisted and formed in any form without breaking it, without causing any stress on it. That is called a membrane, right? If I take this one, I try to bend it, I don't want to do it because it's airy property. You can do it, right? So this is, for practical purposes, this is not a membrane. But if I take the same paper and I put forces in this direction, I can't break it unless I cut it. Right? So this way, if I pull it, this has a very high strength. If I bend it, it has no strength. So that means within its own plane, tent is a membrane, right? Umbrella is a membrane, right? It has good strength in its own plane, but it has no strength in bending. So cloth is a membrane. You can fold it, roll it, right? But when you wear it, I can still pull it, it will still not break. But I can bend it, it will not have any stiffness. So a membrane is an element which has no bending stiffness, has only in plane. In plane means if you apply the forces in the plane of the object, it will be quite strong. Sometimes mostly in tension, because as soon as you apply compression, it will buckle, right? It will just go away. Mostly in tension, but can also be in compression. But if I fold it like this, I can now put my cell phone on it, it will be fine, right? So same membrane, which is very, very weak in getting any forces, if I form it in the right way, in such a way that all the stresses are within the plane, it can become a very strong structure. So the thin membranes, when folded in the correct form, in such a way that the forces only lie in their plane, you can create a very strong structure. You know about the elephant and the egg, right? No? If you put the egg in the right way and you let an elephant put the foot on it, it won't break. Because as long as the force is directed through the eggshell as compression. Because of its form, it won't break. But if you just puncture it slightly on the side, it will break. So membranes can be extremely strong structures as long as we match the form of the membrane to the stress directions, right? So that is why membranes are a very, very, I would say, innovative and also very flexible things that you can create. Do you know about hyperbolic paraboloids? Have you ever heard this word before? You have. Last course I said, please remember it. That one guy remembers what I said last time. Hyperbolic paraboloid. It's a nice word. You know, you can impress people with this, right? But you don't remember. Hyperbolic paraboloid. Hyperbolic paraboloids and many other such forms are pure membranes. Extremely strong membranes spanning large distances. Dome is a membrane, can span big areas with thickness as small as 5 centimeter or 8 centimeter. There is a dome in Russia which is so big that if you divide the thickness to its diameter, it is thinner than the ratio between an eggshell and its diameter. It's that thin, right? And it is almost 100 meters in diameter because they make the perfect form for a membrane. So the property of a membrane is that it has only 2 degrees of freedom. Both of these degrees of freedom lie within the plane of the membrane and they are in one x and y. Basically it's just one composed into 2. So when I say this, it actually has 2 components in 2 directions, but basically it's always 1 degree of freedom inside the plane and it can have 2 components. Correct? Is that already clear? So membranes are a very important structural element that we can use, and these are very lightweight elements, lightweight not in the sense of weight but in terms of finite element because they have only 2 degrees of freedom, right? So computation wise, memory wise, analysis wise, they are very efficient to solve. So anything that we can ignore the bending and other degrees of freedom, we can model as membrane. These are very, very good. Now, a shear wall. You know what's a shear wall, right? Elevator wall. Can we model that by using membrane? This is an I-beam, steel I-beam. Can everyone see? Right? Normally we would model this as a line 1 to 2 and then pick the properties to this one, I, A and so on, correct? But actually you could model this I-beam by using 3 membranes. One membrane for top, one membrane for the bottom, one membrane for the web. Because each one of them are locally, although this has a bending capacity, right? It's a bending element and a shear element, but in reality each one of them are carrying only axial stresses or in-plane stresses. You remember last course I told you, tension, compression. So this is carrying compression, this is carrying only tension, this bottom flat. This has no bending, this has no bending, and this is carrying in-plane shear, which is also composed of principal direction, loop here and here. So I-beam, which has a lot of bending capacity and a shear capacity, it's a bending element. Actually, it can be modeled as a membrane, set of membrane, because of the simple fact that ultimately everything is tension compression. So we should be able to model everything if we do it right by using just the membranes in 2D elements of membranes. Now give me an example that cannot be modeled as a membrane. Anything for which you have forces which are applied here, perpendicular to the plane, you cannot do anything with that. That will cause, so if I put this bone here, I don't want to drop it, it will do like this. So now membrane is not working anymore. I cannot do anything with it. I need to have an element which has bending stiffness. Right? I can have it, as long as it is hanging, I have no problem because it is going to produce tension. But if I want it flat, I will need to apply infinite axial force to keep it straight. And that is where the membrane will fail. So, circular pipes, shear walls, beams, steel section, open section, everything like this, which can be divided into surfaces, can be modeled as membranes. Plates, wherever you need to transfer the load which are applied perpendicular to the plane, then you need a plate. Plate needs bending stiffness. So now I need this one. I need something that has stiffness, thickness and stiffness. So if I apply load here, it won't bend. Right? So that means plate is an opposite of a membrane. It has what membrane lacks, and membrane has what plate lacks. So both of them lack something. Plate does not have axial stiffness, so it cannot take axial forces, only can take bending. Right? You know what's a spiral staircase? Right, you know what is spiral. You know, a very nice, beautiful stair. When you walk up, they are curved and they're changing the direction everywhere. That is one of the interesting structure which has both bending and axial stiffnesses are required for a spiral to work, and also torsion and twisting. So every kind of conceivable stress or deformation or stiffness that you need is present in a spiral staircase. And we get shell, which is both these degrees of freedom plus those degrees of freedom. You get a shell element. Shell element is a complete element which has 5 or 6 degrees of freedom. Now I will, this question mark about Ry, I have put with this is a, I don't want to go into too much detail, but just to tell you that this is one of the 2 degrees of freedom that is not understood. That means on a plate like this one, what will happen? We can understand all the degrees of freedom. There is 1 degree of freedom that we cannot understand. That means if I have an axis here, and if I rotate this around this one, distort it around this one, what will happen to this thing? We don't have that stiffness properties. Just like we have warping in beams, this is a similar thing. So some people ignore it, some people take it infinity. Somewhere 2 approaches can be used, but normally we just think that this cannot be freedom. So a shell element, we have 5 degrees of freedom, bending and axial. And of course shell element is very, very powerful, and you can always use shell element, and it will have both the plate and membrane in there. 2-dimensional elements. So the 2-dimensional element can be 4 loaded, can be 5 loaded, that might that. In the past, there was a lot of research, as I mentioned to you before, about on elements. Every thesis, master and PhD thesis, used to be about defining new better elements to use least memory. So 4-node element, then better 9-node element, 10-node, 8-node and 9-node element, because they were more efficient. Now we are not using them so much. Instead, we use mostly 4-node elements, use more of them. So you want to do curve things, you divide it into 4. Instead of using 1 element, you use 4 of them. Model the same thing, right? Because computation-wise, this element and this one, 4 and this one, nearly the same now. right? So primarily we use now 4-node elements like this, and model almost everything by using 4 or 3-node elements. Now I would like to show you the difference between using the different types of elements for different things. This is shell. I modeled this table by using shell elements. I modeled this table by using plate elements, and I modeled the same table using membrane elements, and I put my phone on the table center. And this is what happens when you put the phone here on a shell element. It is stable, it can carry the load to the columns. When I use plate element and I put the phone on the top, it can still carry. When I model it by membrane element and I put the phone, it falls down. It just goes through. Because membrane element has no stiffness, so it cannot support my phone. So it just falls down, as you can see, it just fell down. So this tells you basically what you can do for loads applied perpendicular to the plane. This shows you what you can do if you apply horizontal load to a wall. So now basically I am taking this one like this, shear wall, you were saying, and I model it by 3 different elements by using membrane, shell and plate. This is what happened when I use shell, no problem, it can take the load. This is what happened when I use plate, because no in plane, it just runs away. And this is what happens when it's membrane, it stays there. So for in-plane loads, shear wall, plate, shell and membrane will be most okay. Shell of course will be okay all the time, but membrane will be just fine. For out of plane loading, plate and shell will work, membrane will not work. Clear? So once you model these things, this can be modeled by membrane. Below portion, this has to be shell because there is water inside, which is going to put pressure on the tank. So the lower part of this shaft, which is only going to have axial stresses and bending, can be membrane. But upper part, this needs to be shell because you're also going to have water pressure on causing bending on these plates here, on these plates here. Right? But this cylinder can be membrane because water pressure will only impose tension in the ring, which is in plane. Right? So this is a good example where you could mix up these kind of things. So now next is a detail of the membrane element, how many degrees of freedom, what goes on there, applications, like that. Please read that. I already explained that. This is how the membrane element really looks like. There are U1, U2, and third degree of freedom. Just like I mentioned, it's not clear. So we don't know. And this has been a problem for software users for a long time because if I use plate element for this tabletop, plate element you will see has no rotational degree of freedom. This one, R3, plate and membrane both don't have it. So when I bring a column there, column has torsion. So when I connect the column to this and this node, the torsional degree of freedom of the column is now lost. It is not connected to anything. So the column will start to spin on its axis. This is called a phenomena orphan degree of freedom, which I will talk about later. We can also use the 2D element or plane stress or plane strain or membrane elements in things that you normally do not consider. For example, walls, as I mentioned to you. So you can use walls, right? Shear walls and all kind of walls, as long as the forces are in plane, but it will not take wind. because that is out of plane. As long as it is in plane, we can use 2D elements of the plane strain or plane stress, which are both membrane of two different types. We can also use a dam and model the dam by using similar technique, because all the sections are the same. Now, there are two interesting things here. In this case, perpendicular to this element, the strain is 0. There's going to be no strain in this direction because it's discontinuing. So you can cut that out. Here, the stress perpendicular to that is going to be 0. There's no body outside, right? So either way, if the strain is 0 or stress is 0 perpendicular to that, you can model it by the membrane type of element. If any one of them is not true, you cannot. Jet element looks like that, and again, this one U3 and R3 is missing, so that's the problem. But you have no rotation, that is, it has 3 degrees of freedom. Shell element, all 6 degrees of freedom. R3 is questionable, but now program just lock it somehow. They play some trick and do it. So that's shell element. Local coordinates are very important for 2D elements. 1, 2, 3, like that. So from 1 to 2 and 3 will be perpendicular to that. Your thumb is 3 and here this is the right hand rule. So 1 to 2 and 3. Third axis is very important because that determines the application of the loads. If you apply the load here or downward, the direction will depend on the third axis. And also the stresses and everything, positive, negative faces will depend on. So the faces which are on the positive 3 axis are positive faces. Face which is below that is a negative face. So for application of loads, it's important to know what are the local axes. So local axes depend on the numbering. So if you do the wrong numbering, local axis may come down. Because 1, 2 and 3, and if you number it this way, then it will become 1, 2 and 3. Meaning will change, loading will change. That's why it is very important to model the things. So 1, 2, 3, 1 here, 1, 2 and 3, 3 is going that way. So this will mess up your model. So we must make sure that we use the same direction. Otherwise, some of your element will be facing down, up. When you apply the load, everything will be messed up. That is why in the programs they have an option to show you the axis 3 by color. So all the elements must have the same color. So when you complete the model, go to that option and see local axis and you will see the color. So if some color is different, normally red and yellow, so all the upward faces must be red. If one of them is yellow, that means negative face. You must correct the order of that element. These are the things that you need to be careful about. This is a typical element in SAP and ETABS. So axis 1, axis 2, axis 3, face number 2. So all faces are marked phase 1, phase 2, phase 3, phase 4, phase 5, phase 6. So these phases are important for applying stresses, forces, loads, understanding results. Even though shell has no, as a 2D element, it still has thickness. So they create it like that, right? But it is modeled only at the mid plane, not model the whole thing, right? So SAP and ETAB have a funny way of numbering the nodes on the element, which is not followed by any other programs or the books or what Dr. Panchal will teach you. Normally, you number things node number 1, 2, 3, and 4, same direction as that. Not these guys. They say 1, 2, 3, 4. This is not good. This is a twisted element, but they have been using it for a long time. Triangular element, we just used 1, 2, and 3 and 4 become 1. We just use 2 nodes at the same time. So again, instead of creating a new element, triangular element, ETABS and SAP people just use this 4 node element and just join two nodes at one point. So it makes programming easier because you don't need to deal with two elements, you only deal with one element. Other programs have many types of elements. Triangle separate element, quadrilateral separate element, but in these programs they use only one type of element. And if you put the same node 3 and 4 at one location, it will become a triangle. Right? So you need to understand all of that to use these programs. Now, what are the section properties we need for a 2D element? What do we need? How many properties we need for line element? 7 degrees of freedom, you need 7 properties, plus moment, plus elastic modulus, 8 properties to define a line element. The element is very simple, but you need 8 properties, or at least 7 if you want to ignore warping, right? Then you go to the modeling of the plates. How many properties do you need? Two-dimensional elements, how many properties do you need? Just thickness plus E and G and maybe mu, so maybe 3 or 4, right? Because G can be calculated from E. So mu. So basically thickness, E and mu. These, what is mu? Correct. So you need those, and then you define this one. That means in two-dimensional element, we do not need that many properties. The things become easier. You don't need to calculate so many properties anymore, because you are now physically modeling something, and you only need thickness and a couple of more elements, properties, right? But material properties become more than geometric properties. In a line element, geometric properties are more than material properties, which tells us something interesting. For line element, we cannot do much material modeling, right? Only E is primarily what you can change. But in here, you can manipulate by using the Poisson's ratio and E, 2 more properties. So you get better modeling capability. But only thickness is enough. You don't need anything else. Alright? A symmetric solid element is an element which is in between 3D and 2D. It is not 3D, it is not 2D, it is something else. Right? This is an interesting element. Powerful, yet not so much known, well known. Hidden element in between 2 and 3D. So what can be a hidden element which does that? This is a cylinder, thick cylinder, right? It could be anything which is like that. Okay, this one, but only with a hollow inside, okay? Just like this. So, if you look at one cross section of that, same cross section is being replicated everywhere. So it's completely symmetrical about its axis, correct? So this section, if I cut a section here, this slice is going to be exactly the same around the entire cylinder. So if I want to model this, I only need to model this element and tell somebody that this element goes around 360 degrees around an axis. That's it. I do not need to model all the sections because the stress in all the sections, or let's say pressure inside, is going to be the same. I do not need to model all the sections and create a solid mesh out of this one. So I just need to model one plane, plus saying that this is symmetrical about some axis. It is just like membrane, only it has this tendency that you have this element and it goes around some axis with an angle theta. So it's a semi-solid element with only one plus property about the symmetry axis. So just only know that, because we are not going to use it in probabilities. If it was a finite element course, I would tell you more about it. Now we come to solid element, the last one. Solid element, as the name says, is a real element. That means this has no more simplifications. It is like this. It means we can just model the real thing as it exists. Like pieces of clay or block, right? You construct it. Real, like a Lego. Each Lego piece is one element. So if you want to make the wall of a house, then you put Lego pieces. So you can consider each Lego piece to be one solid element. So you can construct the entire model from pieces, each piece being a solid by itself. So the perfect example will be Lego. So Lego pieces or Lego blocks are a perfect example of how you can create a complex structure from solid pieces, right? So on top of the Lego blocks may be all of the same height at each corner. Our solid element is more flexible. So each height at each node can be different. So you can actually make a distorted solid element as needed. Now what is interesting in this solid element is that if you look at this top element and this bottom element below, they are actually two shell elements. One here, one top, connected to each other. And that is very interesting because now we can convert a shell element model to a solid element very quickly, or a solid element to a shell element very quickly, right? And that gives you this great ability to create more complicated models where shell and solid can be mixed together, and shells can be converted to solid, and solid can be converted to shells, and that is very, very nice. Line element needs 6 geometric properties, 1 material properties in general, or 7 properties plus 1. Plate, shell or 2D elements need 1 geometric properties, which is thickness, plus 2 material properties, which is the E and mu. Alright? How many geometric properties solid element will need? Zero. You do not need any geometric properties for solid element because you are physically modeling it. I tried to explain to you. Line element, physical modeling is very little, so properties have to be more. Two-dimensional physical modeling is more complete, dimensional properties become less. Here the physical modeling is complete, geometric properties 0. Right? No properties needed, only material properties are needed. How many material properties are needed? What are those 3? No modulus. Modulus does not exist. Only 3 plastic modulus in each direction can be different now. That's it. You can't have shear modulus because you don't have corresponding shear stiffness. There is no stiffness here anymore. Only axial. Nothing. 3 degrees of freedom. Only axial. No bending, no torsion, no warping, no nothing. Only 3 degrees of freedom for each node to move this way. Everything else is determined by the distortion of the element and stretching and twisting, because this is physical now. There is no concept of moment, there is no concept of shear, there is no concept of torsion, there is no concept of warping. There is nothing left except axial, 3-directional stresses and strains. That's it. So we come back to my original thing, that is nothing in the world except tension and compression. and three stresses. Shear, torsion, bending moment, warping, everything is made up. It doesn't exist. They are made up because we create some reference axis. There is no local axis. There is no axis. Everything has disappeared. Can you see that? That there is nothing left in 3D modeling. It's just real object as it exists. No need to define any more reference systems or simplifications or axes or notations. Nothing. Because we are modeling it as it is. All these simplifications are needed because we cannot model something. So that's why solid modeling is really good, really nice. It can serve many purposes as long as we know how to do it. And it has very few properties, no dimensional properties, only material. But material can be very complex. Now we can model, come back to my original thinking what I was telling you about. Dam, water, gates, soil, all modeled as solid elements, right? And soil also, you can model layers of soil, sandy layer, clay layer, different layers, right? Even air can be modeled above that. Why not? Air is nothing but solid elements with its own properties. People do that all the time. How do you think the weather forecasting works? 3D modeling of air, volume. Okay, so which means solid element can actually model everything if we want to do that. And all we need is E, an estimation of E. 1, E2, E3, and if it is same E, one value, if they are all equal. Boundary conditions and supports. So far we are talking about modeling of the structure. What happens when the structure ends? What do we do there? Does the structure really end? We talked about it last time, that it doesn't really end. Because structure ends, air starts. So in continuum, there's nothing, there's never nothing, there's always something. So if there's always something, that we must be able to model it, we should model it, right? So when the formation ends, the soil begins. Soil begins and water below and magna and mental or whatever below that, right? So it's just our idea of where we want to cut the boundaries of our model. So we say we can decide to cut it anywhere, but we should understand what is beyond that. So what did we consider that? So that brings us to modeling of the boundary conditions. Simple one, the simplest model, minimal model is to represent the boundary by springs, which incorporates the stiffness of the supporting system, and we replace the boundary by equivalent springs. So we could have air springs on the side representing air, but the stiffness is so small that we can ignore it. But airplane people cannot, right? For them it is important. Same is the case with liquid. Normally in the water, we can consider the water as a loading, but for the dam, water is not a loading. It is different. It is interaction. So they have to model the water. In fact, in a water tank that I showed you before, the sloshing of the water, movement of the water will interplay with the national periods and movement of the tank. Dr. Finite must have told you about water liquid tuned dampers, right? Sure. So if you have liquid tuned damper, how do you model liquid tuned damper unless you model that whole thing also? Right? So you need to do that. So you can replace the boundary by springs, that is minimal. So if it is a node, you can put a spring here. Let's say this is a basement, right? Then there's a soil here. You can place the soil as springs at the node. Boundary, you can put very simple point boundaries, which do not exist, but you can assume it is like that. It's fine sometimes, as long as you can model it, or you can apply loads there. So you can see the nodes give you the ability to apply the load, use the artificial boundaries, use the spring boundaries, and you can create the model depending on what you need. So it could be that the soil is represented by load for the pressure that comes from the soil, or it could be that the soil is represented by a spring because the soil is supporting your structure. So which is happening? What is really going on? Is the soil pushing the structure as a load, or is the structure resting on the soil as a support? So it's very complicated to model the interaction between structure and soil. And an earthquake is very different. At rest, structure is at rest, but when you apply the wind load, earthquake load, structure is moving, it's hitting the soil. So what is what's going on now? Okay. So these are complex issues which still need to be considered. And sometimes we just ignore them and simplify them. Joint results, we can get reaction forces, you can get displacements of the joints. So if you apply a load, if you allow it to move, you can get displacements. If you lock it, you get result, you get the reaction. Using constraints, last time I told you about, you can use constraints, connect degrees of freedom together so that they move together, right? So this is how you can constrain things, like for example, and then represent them by a few degrees of freedom. So we can constrain those, and this is only left with 6 degrees of freedom rather than 3 compared to 6. So you can combine certain degrees of freedom and consider them equal. For example, here, this one and this one, this R1 and R2 can be the same. So you can reduce them to few degrees of freedom, right? So these are called constraining, to reduce degrees of freedom to model certain behavior. Simplified and also efficient modeling. Floor diaphragm constraint. The entire floor is, no matter how many elements you have, the entire floor is constrained by 3 degrees of freedom. So no matter how many slabs, how many elements, how many things you have, only 3 degrees of freedom. So a 36-story building or 30-story building, 90 degrees of freedom. That is what we used to do because that's all you get in a computer. You can't put a million degrees of freedom like we do now, right? We mesh everything unnecessarily. Rigid constraints, body constraints, use of constraints in beam shell analysis. So you can create the constraints between this one and link them together. So very few degrees of freedom can be used to present the cross section. This was a very, very nice model developed actually by Professor Wasser. What's that called? Thin shell element. They developed that thin shell element. And thin shell element was very nice. You could model the entire wall and box girders and shear walls by very few, by just the center line and the cross section, and the whole thing will be modeled correctly because of this constraint modeling. You can also constrain things together to represent complicated openings and walls. Instead of using that big model of thousands of elements, you can just use a simpler line model to represent that wall by looking at how it is done. This is taken from the book by Professor Ram, I think. Yeah. Use of constraints for mesh transitions. This is very, very important and very difficult problem that has now been solved. Problem is like this. If you create, let's say I want to model a beam, this is a beam, and I'm going to model it by solid elements. I don't want to model the beam by line element. I don't want to model the beam as a membrane element. I want to model the beam as solid element because it's a concrete beam. So I chop it up into small pieces, Lego pieces, because I want to understand what's going on inside the beam. Not only the overall bending moment, I want to calculate stresses deep inside, strains and everything. So I will model it by solid element. And I am more interested at the corner or at this location and not interested so much there. So here I want a fine mesh. Here I don't care about the mesh so much. I just want to model it. And this is quite normal in finite element that your mesh becomes finer where you have stress concentrations, where you want to study more in detail, and the mesh becomes less fine where you don't need the results. So the problem is that if at this intersection, this interface, you will get on one side you will get 1, 2, 3, 4, 5, 6 elements, and on this side you will only get one element. Now, if Dr. Panchat may have told you to connect the finite elements together, you must connect them at the nodes. You cannot connect the elements in the middle. So, which means that this element 20, this one, and this one will not get connected to that element because there is nothing there. So, you will have a gap here. So, a crack or a model will separate. Only these corners will be connected, and this one is not a complete model. But if you use constraints between these elements and these lines, we can connect them together by invisibly gluing them, by using an invisible zipper or a glue, right? Just like a glue, you glue them together, and that glue is the constraints. So if you know how to do the constraints, we could create a constraint between them so that they act together, even though they are not directly connected. Orphan degrees of freedom, as I mentioned. What does it mean, orphan? English language word, orphan. No parents. So we are talking about degrees of freedom which have no parents. Poor guys. Because when you connect one thing to the other, the degrees of freedom are not matching, and some degrees of freedoms do not get connected anywhere, and nobody is taking care of them. So they become orphaned. And those need to be then connected somehow with each other. And this is a problem that has faced the modeling people when you try to connect frame element to shell element and line element to solid element and so on and so forth. You get a lot of degrees of freedom that get lost. For example, this is a clear example. You have a footing which you may be modeled by shell element or plate element, right? And then you put a column on it at this point. You will think this will connect, but actually the torsional degree of freedom from the column does not get connected to the degree of freedom at the plate because there is no degree of freedom present there. So the column starts spinning. You get wrong results. You don't know what happened. Similarly, if this is a solid element and you put a column on the top, on the corner, this will fall down because solid element has only 3 degrees of freedom, only displacement, no bending moment concept. So the bending moment in the column will not connect, so the column will just fall down, right? Similarly, if you try to connect a shell element to a solid element, here shell element has bending moment, capacitive capability, solid element has no bending moment, so this will fall down. So you would think that you can connect a slab to a solid element, but no, it won't, it just falls down because there is no degree of freedom connecting that. So these are the things that you need to be careful when you connect elements together. Look at the degrees of freedom. That's why I had this whole course, this whole lecture, so you understand that degrees of freedom, when you connect them, what is possible, what is not possible, what is allowed, what is not allowed, and how to handle it. CSI have come up with a nice way of solving many of these problems. They call it a zipper element. So if you connect two things together which are not compatible, you put a zipper there, like a constraint. You just weld them, you just put a glue there, right? And then they figure out how to connect them together. So using these zipper or line constraints or edge constraints or body constraints or this kind of elements, they solve many of those problems that you otherwise have. So you practically, you can model anywhere, you connect things, even if they're not connecting, you just put a welding line there and they figure out a way to connect for you. So sad. Next time.